Welcome to the 16th lecture of module 5 on mass transfer operation. In this module, we are discussing distillation operation. Before going to this lecture, let us have brief recap on our previous lecture. In our previous lecture, we have mainly considered minimum reflux, and we have seen how to determine the minimum reflux ratio. The second thing, we have considered stages and reflux for a particular separation. And finally, we have considered the feed tray location. So, in this lecture, we will continue our discussion on multi-component distillation. In this lecture, we will mainly consider batch distillation of a multi-component mixture. And we will try to discuss the fundamental concept of multi-component batch distillation and try to solve an workout problem. So, multi-component batch distillation, let us consider L moles of a solution containing components 1, 2, 3 and so on up to n number of components, and these are having mole fractions x1, x2, x3 and so on up to xn respectively. Now, the moles of the individual component in the solution we can calculate. So, the moles of the individual components in the solution are L1, which would be L x1, L2 which would be L x2, L3 which would be L x3 and so on up to Ln which would be L xn. Now, assume the solution is ideal. Now, the relative volatility alpha I j, that is relative volatility of component I with respect to another component j is taken as constant. Now, further take component j as the base or reference component. So, component j as the base or reference component to which the relative volatility of any other component in the mixture is defined. So, let us do the differential mass balance. Now, if we do the mass balance for component I, it would be minus d L I is equal to y I d star d L. For component J, we can write minus d L J is equal to minus y J d star d L. Now, from these two equation we can write d L I divided by d L J would be equal to y I d star divided by y j d star, and then we can write this is alpha I j. Alpha I j is the relative volatility of component I with respect to j into x j into x I divided by x j, which is equal to alpha I j into L I by L j. Now, integrating from the initial to the final state, we can obtain ln L I initial divided by L I final is equal to alpha I j ln L j initial divided by L j final. Now, the equation which we have developed by the integration, this can be written for all possible pairs with the component j as common to get the following equation: L I initial divided by L I final to the power alpha j I is equal to L j initial divided by L j final, and so on. You will get ln initial divided by ln final to the power alpha j n. This is because since alpha I j is equal to 1 by alpha j I. This above equation which we have derived together with the condition which we know for this system components, for these components can be solve the multi component batch distillation. So, the above equation together with the condition x 1 plus x 2 plus x 3 and so on up to x n would be equal to 1 can be used to solve multi component batch distillation. Let us look into an example and how we can implement this equation. A mixture of 0.25 kilomole N pentane, which is component 1, 0.35 kilomole N hexane, which is component 2, and 0.40 kilomole N octane, which is component 3, is batch distilled at 1 atmosphere pressure to remove 90% of N pentane, that is normal pentane. Now, calculate the amount and composition of the distillate. The Antoine equation can be used to calculate the vapor pressure. The Antoine constant are given in the table. So, this is the table where we will get for N pentane, N hexane and N octane the Antoine constant. The K values can be obtained from the de Priester chart. So, this is the chart which are given and available in the standard book. So, let us write down the components and their compositions given. So, N pentane component 1 which is 0.25 k mole and call as L1 in. N hexane component 2 as 0.35 kilomole and call as L2 in, and N octane which is component 3 and having composition 0.40 kilomole which is L3 in. Now, we can calculate the average molecular weight. So, M average would be equal to 0.25 into 72 is the molecular weight of N pentane, then 0.35 into 86 plus 0.4 into 114. So, this would be about 93.7. Now, taking N hexane as reference component, so from Antoine equation we can write ln Pa B is equal to A minus B by C plus theta. the pressure here is 1 bar or 1 atmosphere, which is 760 millimeter Hg. Now, if we put the Antoine constants which are given over here for N pentane, it would be ln 760 would be equal to 15.9155 minus 2738.42 divided by 226.1 plus theta. So, if we solve this thing, it would be 6.63 minus 15.9155 would be equal to minus 2738.42 divided by 226.1 plus theta, and from here we can obtain theta is equal to 68.8 degree centigrade. Now, similarly, for N pentane we can obtain the vapor pressure, that is ln P1V would be equal to 15.8365 minus 2477.07 divided by 233.21 plus 68.8, which we have obtained for the reference component. Now, from here we can obtain ln P1V is equal to 7.634, and hence we can get P1V is equal to 2068.44 millimeter Hg. So, which would be about 2.756 bar. Now, for N octane we can write ln P3V would be equal to 15.9635 minus 3128.75 divided by 209.85 plus 68.8. So, from here we can write P3V is about 113.892 millimeter Hg, which is 0.152 bar. Now, we can calculate the relative volatility. Alpha 12 would be P1V by P2V, alpha 32 would be P3V divided by P2V. So, if we substitute the values of vapor pressure we have obtained, it would be 2.756 divided by 1, and this would be equal to 0.152 divided by 1, which is equal to 0.152, and this would be equal to 2.756. Now, we can obtain Kr, that is reference component K values, would be equal to 1 by 2.756 into 0.25 plus 1 into 0.35 plus 0.4 into 0.152, and if we do that, we will obtain the Kr is 0.948. Now, if we use this Kr, so this revised Kr we can use, Kr would be equal to P2V by P, which is equal to, we can write 0.948 would be equal to P2V divided by 1. So, from here we can write P2V would be equal to 0.948. Now, if we recalculate the boiling point of N-hexane at this pressure, so recalculating the boiling point of N-hexane at P2V, we can obtain ln 711 would be equal to 15.9155 minus 2738.42 divided by 226.2 plus theta. So, from here we can calculate theta plus 226.2 would be about 292.91, and hence we can calculate theta would be 66.715 degree centigrade. This is the boiling point of the reference component. We have amount of N-pentane to be removed %90 of 0.25 kilomole, which was in the feed. So, this would be 0.225 kilomole. So, the amount of pentane remains is 0.025 kilomole. Now, at 66.715 degree centigrade, we can calculate the vapor pressure for component 1 and component 3, that is pentane and N-octane. So, ln P1V would be equal to 15.8365 minus 2477.07 divided by 66.715 plus 233.21. So, this would be P1V would be about 1953.8 millimeter Hg, which is about 2.6 bar. Similarly, ln P3V would be equal to 15.9635 minus 3128.75 divided by 209.85 plus 66.715. Then we can calculate P3V from here would be equal to 100.64, which is millimeter Hg, which is equal to 0.139 bar. So, K1 we can calculate is equal to P1V divided by P2V, which is equal to 2.6 divided by 0.948, which is equal to 2.74. K2 is 0.948 and K3 similarly we can get 0.1466. Once we obtain K1, K2 and K3, we can obtain alpha 21, which is equal to P2V by P1V, which is equal to 0.364. Alpha 12 is 2.74, alpha 23 is P2V by P3V, which is equal to 6.466, and alpha 32 is 0.1466. Now, we can check the values of Ki xi, summation over I is equal to 1 to 3. So, this would be 0.25 into 2.74 plus 0.948 into 0.35 plus 0.4 into 0.1466. So, which is equal to 1. So, that means the temperature which we have obtained is correct as a bubble point. Now, assume bubble point is equal to 95 degree centigrade. At this temperature, from this de Priester chart, temperature and pressure at the initial pressure of the system is 1 atmosphere, that is 101.3. From this temperature and pressure, we can obtain the values for N pentane, N hexane and N octane, the K values. So, if we use the chart, we will obtain K1 is equal to 4.65, K2 is 2.03 and K3 is equal to 0.45. Now, we can calculate alpha 21 would be equal to 2.03 by 4.65, which is equal to 0.437, and alpha 23 would be equal to 4.51. Now, if we use the average values of alpha, we can write alpha 21 would be equal to 0.364 plus 0.437 divided by 2, which is equal to 0.4005. Similarly, alpha 23 would be equal to 6.466 plus 4.51 divided by 2, which is equal to 5.488. Now, L2 in divided by L2F initial and final would be equal to L1 by L1 initial divided by L2 L1 final to the power alpha 21 would be equal to L3 initial is L3 final to the power alpha 23. Now, if we substitute the values 0.35 by L2F would be equal to 10 to the power 0.4005, and from here we can obtain 0.139. This 10 is the ratio of L1 initial divided by L1 final. L1 initial was 0.25 kilomole of N pentane and the remaining which is final is 0.025 kilomole. So, the ratio L1 initial by L1 final is 10. Similarly, if we consider L2 initial by L2 final with respect to L3 components over here. So, we can obtain L3 initial divided by L3 final to the power 5.488 would be equal to 10 to the power 0.4005. 0.4 divided by L3 final would be equal to 1.183, and from here we can write L3F would be 0.338 kilomole, and this is L2F is equal to 0.139. Now, to check the assumed final temperature of 95 degree centigrade, let us consider the number of moles at the end. So, we need to check for the assumed final temperature of 95 degree centigrade. So, total number of moles at the end which is equal to 0.025 plus 0.139 plus 0.338. So, which is equal to 0.502. So, the mole fraction we can calculate x 1 is 0.0497, x 2 is 0.2768 and x 3 is 0.673. Now, if we calculate summation over I is equal to 1 to 3 k I x I, which is 4.65 into 0.0497 plus 2.03 into 0.2768 plus 0.673 into 0.45 which would be equal to 1.095 which is greater than 1. So, the assumed temperature is a bit high. So, what we need to consider little lower temperature than 95 degree centigrade. So, let us assume or calculate the revised K values. So, taking our revised K values, that is K 2 would be equal to 2.03 divided by 1.095 which is 1.85, and then from the chart we can obtain the corresponding temperature which is equal to 91 degree centigrade. So, at 91 degree centigrade K 1 is equal to 4.4 and K 3 is equal to 0.39. So, we can calculate alpha 21 which is equal to 1.85 divided by 4.4 which is equal to 0.42, alpha 23 which is equal to 1.85 divided by 0.39 which is equal to 4.74. We can calculate the average alpha values, that is alpha 21. Alpha 21 is equal to 0.364 plus 0.42 divided by 2 which is equal to 0.392, and alpha 23 would be equal to 6.466 plus 4.74 divided by 2 which is equal to 5.6. Now, recalculating the values, we can write L2 initial divided by L2 final would be equal to 10 to the power 0.392. So, from here we can calculate L2 final would be 0.141 kilomole. Similarly, if we consider L2 or L3 in divided by L3 final to the power 5.6 which is equal to 10 to the power 0.392, and from here we can get L3 F is equal to 0.340 kilomole. Now, the total moles in the final liquid we can calculate. Total moles in the final liquid which would be equal to 0.025 plus 0.141 plus 0.34 which would be equal to 0.506 kilomole. Then we can calculate the mole fractions. X1 would be 0.049, X2 would be 0.278 and X3 would be 0.672. So, now we can calculate summation over k I x I is equal to 1 to 3, which would be equal to 0.049 into 4.4 plus 0.278 into 1.85 plus 0.672 into 0.39. So, this would give about 0.99, which is close to 1. So, the estimate of the final temperature that is 91 degree centigrade is good enough. And hence the composition we have to calculate. So, the number of moles in the distillate would be equal to 1 minus 0.506, which is 0.494 kilomole, and then composition in the distillate would be x 1 d is equal to 0.455, x 2 d 0.423 and x 3 d would be 0.1185. So, this is how we can solve batch distillation problems. Thank you for attending this lecture as well as the mass transfer course, and this is the end of our lecture for all the modules. I hope you have enjoyed the course. If you have any queries, we can sort out during the online discussion. Thank you very much.